Hello, everybody, and thank you for inviting me to present in this meeting. I'm really happy to be able to present some of the stuff and some of the thoughts that we have been doing inside Atmel, also to support this forum and also to support the use of Verilator and to get more people into that community. I'm here together with the development team in Trondheim. We have been working with simulator techniques for a number of years, and we switched to Verilator a year and a half back. You can all see my screen properly, I guess? Yes, you can. So as a background, I mean, as you probably know, Atmel is a major provider of 8 and 32-bit microcontroller solutions. We have the AVR proprietary architecture for consumer and industrial 8-bit devices. We are utilizing ARM, particularly Cortex M4 architecture for 32-bit devices. We have the MaxTouch proprietary architecture for capacitive display touch applications, which has become very, very popular in the mobile industry. And we also specialize in power technologies, CPUs, and devices with very, very low power consumption. The latest offering in that respect is the SAM4L. At Atmel, we use microcontroller tools as a primary marketing channel for our devices, based on the simple fact that developers often get to decide which devices they will take into their design and hardware offering. And if the development environment is easily available, inexpensive, nicely executed, and instead of being a pain, developers will tend to stay with that, and they will happily use our devices. So it's a very, very simple thought behind it. One of the major components we have, besides a whole range of hardware tools, is the Atmel Studio, which is a complete integrated development platform with more than 100,000 users worldwide. We have just recently provided the Atmel Gallery, which is a place to sell or distribute open or free extensions for the Atmel Studio. You can extend the functionality in any way, shape, or form. And you have a distribution path that can either be for non-commercial or commercial application. There's also a payment solution embedded. And we have also just recently opened the Atmel Spaces, which is a collaborative workspace that integrates into the Atmel Studio. So this is the background for our interest. We are using the Verilator and the simulator concept in a little bit different fashion than was described as the primary usage of the Verilator. We use MCU simulators as a debugging tool for customers doing application development. We are not using simulators, or at least simulators based on Verilog, to validate IC development. And we do not use simulators in complete system simulation fashion because that is too slow. We are using simulators as a target where the customer can validate C++ or C++ code before they actually deploy the code on an actual hardware target. And this is very valuable because if you look at the normal development timeline for the product that our customers make, you tend to see a higher and higher integration level on the MCU itself. So if you look at the modern microcontroller, in the basic applications, you don't even need to attach an external crystal. It's enough to power up the device, and you actually have your complete subsystem with communication channels, I/O ports, analog inputs, digital inputs, and internal crystals. So it's a complete system on a chip, which means that hardware development times are actually, to some extent, going down. While if you look at the software complexity running on the devices, you will see that the software complexity follows Moore's law now, that it doubles in complexity or even more every 18 months. So the software firmware development timelines takes you to outshadow the hardware development timelines, which means that it's really, really valuable for customer to start debugging the actual software firmware before they have hardware targets present. So what we do is that we use the Verilator and we use the code base of devices, and we make simulators based on that are integrated as targets in the Atmel Studio integrated development environment. And the development environment does not see a difference between the simulated target nor a physical target if you use external debugger. If you are going to make this scenario work, we need cycle-accurate simulations of a complete device, including memories and all peripherals. And the easiest way to achieve this is actually to reuse the same code that was used while creating the device in the first place. Another challenge that we see is that the microcontroller market is divided into a lot of sub-markets, and price is really a key issue in many of these markets, which means that the way that companies like Atmel actually survive in the market space is to make microcontrollers that are spot on dedicated to a certain segment. You have to have the right CPU power, you have to have the right peripherals, you have to have the right memory size. You have to target that in order to get a die size as small as possible so that you retain some profit margin yourself, which means that at the time of writing, we have more than 350 models or 350 actual devices that are sold to the market. And if a customer wants to use a simulated module in a certain project, we need a simulator, not as a generic simulator for that particular architecture, but we need it specifically for that device, including all the peripherals and the correct memory sizes and so forth. So this is a challenge. I thought I was going to break off here and just show how this actually can be used. This is the third page that you come to if you install the Atmel Studio. Atmel Studio is a free development tool. It can be downloaded from atmel.com. It's a real bargain because it's a beautiful development tool at a really premium price, $0. You only have to leave your name. So let's say that I want to build a new example project, checking out. So I click on this, create a new example project from the Atmel software framework. I want to have something based on a particular kit. I'm choosing this eval kit that is based on a 32-bit AVR micro. And I want to do a common I/O port example. And I want to create a project based on this. So that's basically what I do. And now I have my software project up and running, and you can see I have my my main section here. You can see I've selected the device AT32UC3, but I have no tool selected. If I click on this panel now, you can see I have no hardware connected. But if I click on this, I can choose the simulator model. If I now chose to go back to my I/O port example, I go to the first. I go to the first procedure in that file. I go inside that. I will set a breakpoint at the first line. I can go to my solution. I can build my solution. Basically, I'm done. I can start debugging. I can start debugging and break. And I can go to the next breakpoint. If I now click on this particular view, let me see here, where does that go? Can you see the I/O? It's all right in that, okay. I clicked on the I/O view, which now means that you can see all the internals, all the internal registers, everything in the device is actually now exposed to you. And this is all run on a model created with the very later toolchain. That was it. If you want to play more with it, you should just download it for yourself. I would recommend you to do that. It's great fun. So we have used with techniques for creating these models for many years, and we have gone through different commercial vendors. We used VTOC. Jeremy, who's online, is quite familiar with that tool chain. Then they were sold and they changed to Carbon Design System. And we used that for a number of years. We will say that the use of commercial tool chains for our project has actually proven difficult. It's a complex and specialized field, which means that there are few customers and a very difficult product to make, which makes them terribly expensive. The companies supporting them tend to be small, which means that they will tend to support their major key customer at any given time. But if you are not that one, you suffer. Some of the companies in the business tend to have business models and license agreements that does not fit very well with the model that we have, namely distributing a free integrated development environment with all the models to 150,000 customers worldwide. And some of the commercial vendors also had business models that makes Atmel a competitor to some of the work they would like to provide to their customers. So after doing this for some years and having these challenges, we decided we wanted to explore the use of open source tools for this development. And as you see, the main advantages are, of course, no license fees, what you pay for going to real work. Tools will be available no matter what happens to the project. We have seen this clearly with some of the commercial tools that we have used before, because when acquisition of the companies has been made, it has made it difficult for us to remain users of the tool chains. No concerns with software license management. That is actually quite nice because we can deploy the tool chain at multiple design locations worldwide without difficult license negotiations that we otherwise would have to go through. We benefit from work contributed by others. We have source code access, and we probably have reduced bug fixing cycle time, even though that is one uncertainty also in this area. But at least if nothing else works, we can pay for having it fixed ourselves, or we can go into it ourselves. Also, I think there's some interesting things related to the psychology of software purchases. I think that the market in general, and so is Atmel, is actually less willing than in the past to buy expensive software. We see software license management as a hassle, particularly when you have to go into negotiations about site licenses that are geographically limited, all these kinds of things. It's only a drag to the process. However, it seems like, and I'm talking for Atmel, it seems that we are more willing to, and I think that is also a general rule, we are more willing to pay consultant fees in order to get specific jobs done that suits our needs perfectly. So I think in this particular segment, an open source model where companies like Atmel pay for feature development is probably more robust than a commercial license agreement model. When it comes to Verilator, Atmel has visited the Verilator project on several occasions. We started this effort back in 2006. I think we visited the tool chain both in 2006 and then again in 2008. At that time, we found the tool chain immature regarding to the needs that we had. But when we revisited the tool chain back in 2011, we found the situation had changed and the tools seemed much improved. And also in cooperation with Endocosm and based also on previous cooperation with German Bennett. And we thought we actually had a way of changing and paying for adaptations to the tool that would make it suit our needs perfectly, and then also remain in control over it since it's an open source tool. So in the last year, a number of technical issues has been resolved, and in addition, we have also paid to have system Verilog support implemented, which should benefit everybody. When it comes to the experience of getting Verilator to work on our designs, I think it's been comparable to what you see in the commercial tools. There's no out-of-the-box working experience here. It's a fair amount of work to actually set it up for your specific device libraries, your coding styles, and the peculiarities that all companies develop when they make their devices. A very, very simplified view of the simulator model architecture. We have on the model side, we provide a set of API functions that are the same for all the devices. We on the layer below that, we have a device-dependent C++ wrapper. We usually take the top level of the Verilog code for the device and replace that with code that is specific for the simulator integration, but then we keep the remaining Verilog code underneath. And as I said, this is also a goal for us. We do not want only the CPU and the instructions to be represented. When you work on microcontroller design, it's actually the peripherals and the way they integrate with the CPU that is the interesting part. Also from an overall efficiency standpoint, but also based on the fact that all the difficult software we write is the software that addresses the actual hardware in the device. And that is the most error-prone part of your software project, and that's where most of the debugging time goes. If you look at the challenge of being an embedded design engineer, and when you are getting your hardware back from the factory first time and you're going to make this work, you have really 3 levels of uncertainty. Your hardware might be wrong, your firmware might be wrong, and your development environment might be unstable. And then you start working and nothing works out of the box. And then you really, in the first round, do not know what to suspect and where the errors are. By having simulators and by being able to actually debug low-level code before you have any hardware, you have the opportunity to take a lot of uncertainty out of the software firmware equation so that you can suspect, for instance, hardware bugs if your firmware doesn't behave properly when you actually get to the first hardware. It takes out some of the parts of the equation for the engineer, and he will usually speed up his development time. So these are the main steps of the model creation. I should really have had some of the guys in the team here to present it because they are much more knowledgeable about the process than I am. But I'll present it from a very high level, 10,000 feet point of view, and the guys can answer questions afterwards if you want to have a real more in detailed knowledge about it. But basically, we replace the top level module. You also must remove the non-synthesizable part of the hierarchy, which are analog front ends. Also, the flash blocks in our devices are non-synthesizable and have to be replaced by software models. We create replacement modules for the modules that cannot be used with the validator, like I said, including non-volatile memories and so forth. We make the design compile with Verilator. This might require minor changes to RTL code through the hierarchy. We create DPI functions to address memories, CPU registers, and I/O codes. This part is a merge of knowledge from the Verilog code base and also from XML descriptions that you get from the IC department. We write the device-dependent part of the C++ wrapper, then we test the compiled model, then we set it up for a production build, and then we actually, when we have the compile, we associate it with the studio build, and then we distribute it together with Atmel Studio. As I said, we have 350 devices to model, so to make a production scenario out of this is one of the most important parts for Atmel. I think it's also actually one of the parts that are still a little bit lacking. We spend too much manual times on making the models. We would like to automate this process further. Challenging task, but yeah, it's things we're looking into. That's what basically it. That was the whys, the strategy behind it, and also to a little extent how we actually implement and use the toolchain. So I think now I'm open for questions.
No questions in Bristol at the moment, so we'll switch to some of the other sites. Cambridge?
Any questions? Cambridge? No, Mike, I don't think we've got any questions here either.
Martin, Eindhoven? Okay, there is one question in Bristol, so we'll switch to our question in Bristol whilst Eindhoven make their mind up.
Hi, it's Carl from Bristol. Do your customers find the speed of the Verlator model sufficient for running big pieces of the code?
No, probably not. If you are trying to do complete system simulations, the speed will be annoying. So I would say at the moment, if you have a large piece of software and you want to simulate the complete functionality of it together with peripherals, I would say that the overall output is on the slow side. And that's why I also emphasize we do not see this as a complete systems simulation tool. We see this as a debugging tool because what you can do with this is to take code snippets. You can debug your implementations towards the register structure of the device. You can look at the nesting of interrupts. You can look at your DMAs. You can look at your ATDs, conversions, and the algorithms. And if you single out all these snippets, you can do a lot of really useful low-level debugging. But for a complete systems simulation, it's on the slow side.
So what's the solution for debugging a big piece of software you would propose? Are you running part of it on the hardware and then saving the state of the system and running only part on it on the suspicious part of the Verlator? Because quite frequently, just to get to the part you are going to debug, you need to run through millions of cycles first.
Yep. I would say that if you need to run through 2 million cycles on a complete system before you actually get to the bug, you should probably rather debug on hardware. If you look at the situation from Atmel's side, this is a tool that is provided to users of devices that are commercially available, and we also provide hardware debuggers that go together with all the devices, and we also provide hardware reference boards for all the devices. So you have an opportunity to actually set up a hardware debugging chain instead and debugging in full speed if that is your requirement. The advantage of the simulated mode is that you can do more advanced debugging concepts, including it gives you the possibility to do all kinds of variable debugs. You can debug part of the code execution by installing CPUs and DMAs and things like that that cannot be covered in the normal debuggers of microcontrollers. And also on smaller microcontrollers, you tend to have very limited functionality in the on-chip debug core. So there's a trade-off. You can do a lot of advanced debug concepts on simulated models, but within smaller domains. But if you're going to run the full system, you better run it on hardware, I think.
Okay, thank you. Eindhoven now. Do you have a question, Martin?
There are no further questions from Eindhoven.
Okay. De Nobel? Francois?
Not too many questions from the audience. I do have one, which is how do you compare the Atmel Studio versus Eclipse in the same thing?
From a political standpoint, I'm not sure if I'm the right guy to answer that, since I've been pushing myself behind Atmel Studio for the last 10 years. If you look at the community that we are addressing, and particularly the target markets for Atmel microcontrollers, we see that the customer base we have tend more to come from a hardware perspective than from a software perspective. The people that come from a hardware background tend to find that Atmel Studio easier to use than Eclipse, simply because the Eclipse is even more feature-rich, but also more bloated in many respects. So that's the feedback that we get through the market research, that from an ISO point of view, we are better. I think in terms of functionality, depending on which controller family you choose to use and where your main point for the debugging is, Eclipse might be just as feature-rich.
Okay, thank you. We're going to switch to some online questions now. Sorry? First one is on licensing. Atmel Studio, is it GPL same as Revelator or not?
Atmel Studio is per se not open sourced. So there's an Atmel license for use. So that is basically a fully functional integrated development platform that you download and install, but we don't provide open source for the entire Atmel Studio.
Okay. A question from Gareth Edwards. Creating DPI functions as part of the workflow, is this pre or post Revelated code?
I have to rely on my design team for this one because I don't know the answer myself, but they didn't understand the question. Can you elaborate a little bit more because they're listening?
Well, for the sake of time, what we'll do is we'll answer that afterwards. We'll send you the question now online, and then if you can come up with an answer online, that might be the easiest way of doing it. Last question. Is all the RTL required for the models packaged as part of the tool or not?
The way that we do this, and I'm not sure if I was clear about that, we take our own RTL code and then we actually use, we do the replacements that we described in the Verilator workflow. Then we synthesize with the Verilator and get up with a C++ code base. Then we compile the code base together with the wrappers and present that as a dynamic linkable library that is a part of the studio. So the RTL code is actually in there, but it's compiled, optimized, flattened, and in a binary form. So there's no way that users can actually see the actual kernel code, and that is also Atmel wouldn't allow that. We are not open sourcing our devices. That is really real trade secrets from Atmel.
Okay, thank you very much. That's the last question. We just got the one we'll do online. So the last thing is just to say thank you very much to Dag and to Atmel for their talk.
Thank you. Thank you.